today we're going to finish our information on chemical bonding. So yesterday in the previous lecture we talked about ionic and covalent bonds, which we'll go back to at the end of this. But today we're going to talk about a third type of bond, and I kind of put here, it's called a hydrogen bond. But it's a very weak bond, and to be honest, it's considered more of an attraction or something called an intermolecular force, or sometimes that's called an IMF. Because unlike an ionic or a covalent bond that holds a compound together, like NaCl that has a chemical formula, or H2O that has a chemical formula, hydrogen bonds do not create compounds. What they are weak attractions between two molecules. Specifically, the example we're going to use is water, because water specifically makes hydrogen bonds with other water molecules. But water is not the only thing on the planet that can make hydrogen bonds. So what happens in water, and they explain this here, is that the hydrogen bonds are attached to oxygen by polar covalent bonds. So in a molecule of water, I'm going to draw it here at the bottom as a reminder. We talked about this yesterday, I believe. So here's hydrogen, oxygen, hydrogen. This is a polar covalent bond. It's a strong bond, a covalent bond. The electrons are being shared, but the reason it's called a polar covalent bond is because they're being shared unevenly. What does that mean? Well, the oxygen is more electronegative, and that's a fancy word that basically means it pulls harder on electrons than the hydrogen does. So oxygen actually has these pairs of electrons sitting over here as well that sometimes are drawn here. And because it pulls on the electrons, I gave the analogy yesterday that if I shared a candy bar with you, but I ate 3/4 of it and I only gave you 1/4 of it, technically, I didn't share evenly. You didn't get half the candy bar, you got less. And that's sort of what's happening in a polar covalent bond. The electrons are sort of spending more of their time around the oxygen and less of their time around those hydrogens. And so the oxygen ends up having this slight negative charge. It's called a partial charge. And it's negative because, remember that electrons are negative. So since the electrons are hanging around the oxygen more, the electrons are creating this slight pull. That's why it's called polar covalent. It's creating like a positive pole and a negative pole, like the North Pole and the South Pole, or like the poles of a magnet. So the oxygen has this slight negative charge. The hydrogens have a slight positive charge, and as a result of that, we get this other kind of bond called a hydrogen bond. Now what happens in the hydrogen bond is this: opposites attract, right? So you have this slight positive charge on this hydrogen, and then over here you have another water molecule over here, and this water molecule also, remember, has these slight charges. Oops, I didn't mean to do that. It wouldn't be positive on that oxygen there, it would be negative. So let me draw that correctly. So on the oxygen here, we have this slight negative charge. Now, opposites attract. So what happens is this hydrogen sort of sticks temporarily to this oxygen. And they draw it as a dotted line, not a solid line, because this is only really an attraction. And this is what they're calling a hydrogen bond. It's an attraction between the hydrogen of one atom. And technically, and you're going to learn this in chemistry next year, but hydrogen bonds only really form between hydrogen and 3 other possible elements: nitrogen, oxygen, and fluorine. But for purposes of our class, we're really going to be focusing on this one, the attraction of hydrogen to oxygen. So it's the hydrogen in one water being attracted to the oxygen in another. And this is basically why water doesn't all float away as a gas. Why is it a liquid? What keeps the molecules together? Well, it's these hydrogen bonds, and these bonds are constantly breaking and reforming around other waters. In other words, these aren't locked in place like an actual bond. So here's a picture. So this is showing one water molecule, and it's actually attracted right now to 4 other water molecules, and these, the dotted lines, are the hydrogen bonds. Now they put here charges as if this has a full charge. Remember, it's actually this little symbol. Looks almost like a figure 8 that didn't get finished, and it means partial So technically these are partial charges, not full charges. Notice it's always positive to negative. It's always a hydrogen and an oxygen being attracted. So what happens in liquid water, because water moves, right? It's not stuck in place. You can stick your hand in it. It swishes around. So this bond breaks, sort of like me and you shaking hands, and just lasts for a second. And then it lets go, and as it floats along, oh gosh, there's another oxygen, and it gets attracted. And then it forms a hydrogen bond with that one. And then that one breaks, and it forms with another one. And so these water molecules are sort of sliding all over the place, but every time a hydrogen and an oxygen from separate waters get close to each other, they temporarily create this hydrogen bond. So this is what's happening in liquid water. And here's another picture of it. And this one properly shows that it's a partial charge. So again, this is not permanent in liquid water. This is temporary. And it's really just a really strong attraction. So don't, even though they use the word bond, don't mix that up with an ionic bond or a covalent bond. This is really just an attraction. And this will form, and then it'll break, and then maybe it floats over here and forms one with this one, and maybe this one forms one with this, the oxygen on this. Remember, it'll never be hydrogen to hydrogen or oxygen to oxygen. It's always the opposite charges. It's always the hydrogen of one and the oxygen of the other. Now, for test purposes, just remember that the bonds within a water molecule that make this H2O, these are the polar covalent bonds. These are strong. These are not breaking. When liquid water floats around, these hydrogens are not breaking off of it. Even when you boil water and it turns into steam and floats away, these bonds are not breaking. Water is water. Steam is still water. Ice is still water. These bonds stay intact. The only bonds that are breaking when it goes from liquid to gas are these, the hydrogen bonds. Basically, the water molecules are getting enough energy to escape the surface and float away free as gas molecules with no attractions to anything else, and they're just floating around. So each water molecule has the ability to form hydrogen bonds with 4 other water molecules around it, but again, these are not permanent. These are very temporary. They do tend to lock in place in solid water, but we're actually going to talk about that another day. All right, last section, or last portion of this lecture is on chemical reactions. So, for example, when water forms from hydrogen and oxygen, or any time matter changes, this is called a chemical reaction. The reactants are always the things on the left. So in this picture down here, these are the reactants. And on the right side, what's made are the products. Now, there's a rule about chemical reactions and about reactants and products, and that is this. It's called the First Law of Thermodynamics. Basically says that matter or energy cannot be created or destroyed. So this matter, chemical reactions, do not create or destroy matter. Energy isn't created or destroyed, matter is not created or destroyed. So then what happens in a chemical reaction? I mean, if I burn a piece of wood, isn't the wood gone? Well, yes and no. It's not wood anymore, but if wood is made out of carbon and hydrogen and oxygen, and they're all put together in a particular way, when you burn the wood basically breaks down into carbon dioxide and water vapor that floats away, the smoke and the vapor, and ash, which is probably just pure carbon atoms that are all combined. That's pretty much what ash is. So the carbon, hydrogen, and oxygen in the wood, it didn't disappear. We didn't create anything. We didn't destroy anything. What we really did was we rearranged the atoms into new molecules. So this is a formula for cell respiration, which is how your mitochondria break down glucose to make energy for your body. So this is not balanced. I'm going to go ahead and balance it. So why do we put these numbers in the front? Well, because the number of carbons going in on the left has to be equal to the number of carbons coming out on the right, because we know matter can't be created or destroyed. So if glucose has 6 carbons and they go into the reaction, then I must make 6 carbon dioxides because I need 6 carbons coming out of the reaction. In other words, a chemical reaction with the reactants on the left and the products on the right show us the proper balance of how the atoms get rearranged. So on the left side, how many hydrogens go into this reaction? Well, 12. How many come out? 6 times 2, because there's 6 waters that are made. Each water has 2 hydrogens, so 6 times 2, 12 come out. They just got rearranged. Now the hydrogens aren't part of glucose anymore, which is what 6C6H12O6 is. Now those oxygens and those hydrogens as well are part of water. So, and we can also count up how many oxygens go in. Well, 6 in the glucose plus another 12 oxygens here, atoms, because it's 6 molecules of oxygen. So you add that up, there's 18 oxygens on the left side of this. 6 of them are part of glucose, and then 6 of these O2s, which are oxygen like gas from the atmosphere. Well, that must mean 18 come out. Let's double check. 6 times 2, so that's 12 oxygens in the carbon dioxide. 6 times 1 is 6. 6 more oxygens in the water. 12 plus 6, 18 oxygens come out on the other side. So, again, chemical reactions, what should you know? Matter's not created or destroyed. It just gets rearranged. The reactants are the things that are on the left side of the arrow. They're the things that go into the chemical reaction. And then on the right side of the arrow are your products. And here's just another picture of the same thing. All right. I put a little periodic table here just as a kind of a summary. So going back, just to summarize everything we talked about atoms and bonding and everything, and we're doing in class a periodic table activity. So the periodic table is arranged by increasing atomic number. As the protons go up, the number on the periodic table goes up. They're also pretty much in order by increasing atomic mass. They get heavier as you go. In addition to that, how do we put them in these groups or families? They are actually by the number of valence electrons. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Now these are called transition metals, and we don't really focus on them in here. We focus mainly on what are called the representative elements, which are sort of the ones that are a good representation of what we see in nature. Over here, they all have 3, 4, 5, 6, 7, and with the exception of helium, 8 valence electrons. And remember that the number of valence electrons determines how it behaves. So if it's in the same group or family, the same column, it'll behave very similarly. Like these, lithium down, are all very active metals. You put them in water and they react violently. They may even explode. All of them, because they all have 1 valence electron. Whereas these over here, except for helium, they all have 8. And remember, that things want to have 8 to have a full outer shell. So these are your noble gases. They're pretty much unreactive because they already have a full outer shell, a valence shell. Hydrogen and helium are the only 2 elements in the whole table that just want 2 valence electrons. Now the rows on the table, these periods, that actually corresponds to how many electron shells they have. So everything in row 1 has just 1 shell. So hydrogen looks like this. This is the nucleus, 1 shell, 1 electron. Helium has 2 electrons in that same shell, and the first shell only holds 2, you should remember from class. Everything in row 2 has 2 shells. So lithium would look like this. It would have 1 shell full, and now 1 electron in the second shell. Sodium, third row, has 3 shells. It would look just like lithium, except it would have 1 full shell, 2 full shells, and then 1 electron in the third shell. Potassium would have 1 electron in the fourth shell, etc. So these periods, these rows, correspond to the number of shells, of electron shells. So the valence electrons, the outermost shells, sort of get farther and farther and farther away. Also, and this will help with the periodic table activity you're doing in class, everything on the left side of the table up to here, this zigzag line I'm drawing, everything up to here is pretty much called metals. They're shiny, they have, they conduct electricity, they're flexible, there's a lot of things about them. And everything over here, these are all nonmetals. So these are all nonmetals. And the things that touch this line, like these, this one, this one, this one, these are called metalloids. They behave kind of weird.